This is section 11.2. Today we're going to talk about how to find the slope of a curve that's defined parametrically and not with a Cartesian equation. So for example, if y equals 2x plus 1, then y prime is 2. But if y is given by, if a curve is given parametrically, x of t, y of t, is there a way to find y prime, dy dx, without eliminating the parameter? And the answer is yes, and we'll see how to do that in a minute. But first, let's do a little bit of review on eliminating the parameter, and then going the other direction, how to parameterize a curve. So this whole first page is review from section 11.1. This is just a reminder of the methods for eliminating the parameter. So if we have this curve here, clearly method 2 is the one we want to use, trig identities. So remember, a parametric curve can be given as one equation with parentheses, x and y in parentheses, or you can write it as two separate equations. X is 2 tangent t, and y is negative secant t. So solve this one for tangent. Tangent t is x over 2. And solve this one for secant. Secant t is negative y. And so we use 1 plus tangent squared t is secant squared t. And we replace the tangent squared with x squared over 4 and replace the secant squared with y squared, because the minus squares out. Now that's a hyperbola, and to see that, let's write it as y squared minus x squared over 4 equals 1. So that's a hyperbola. If it was a plus, it would be an ellipse. But since there's a minus there, it's a hyperbola. And if we set x equal to 0, y is plus or minus 1. So we know it opens up, down. Because I can set x equal to 0 and y is plus 1 or minus 1. And if I try to set y equal to 0, I can't do it. Okay, so what part of the hyperbola are we getting? So now we have to look at the limits on t. When t is 0, x and y are respectively, tangent of 0 is 0, so 0 comma, secant of 0 is 1, so negative 1. So we're down here at t equals 0. We're on the lower branch. And then this is defined for t strictly less than pi over 2. So to find out what direction I'm going in, left or right, let's pick a number greater than 0 but less than pi over 2, like pi over 4. And in this case, we get xy equal to 2 comma negative root 2. So that's going to be going in this direction, because 2 negative root 2 is over here in quadrant 4. So we're only getting a quarter of the hyperbola. All right, going in the other direction, we had a parametrization Bible, and so I've copied down 2 of the formulas in that Bible, the 2 relevant for these problems. This first one is of the form y equals f of x. So x comma y, just reading from my Bible here, I let x be t, and y is f of t, which is 2t squared. And then t goes from a to b. A is 1, and b is 3. So that's that one. For the next one, we have a line segment. So if we use the Bible for line segments, this is my x naught, y naught. This is my x1, y1. I'll write this as two separate formulas rather than one formula with parentheses, one formula. So x is x naught, which is 1, plus x1, which is 3, minus x naught. So 3 minus 1 is 2t. And y is y naught, which is negative 2, plus, I want y1, which is 4, minus negative 2. So that's 6t, and t goes from 0 to 1. Okay, on to the new stuff. If you want the slope of a curve given parametrically and you do not want to solve for y, you can use this formula right here. dy dx is dy dt over dx dt. And you should memorize that. And you'll use it all the time. For the second derivative, you don't have to memorize that formula. Here it is. And it's a little bit different than the one in your book. Your book has, I can't remember, d by dt of y prime over dx dt. But the question is, what is y prime? Is it dy dx or dy dt? So the book's formula is a little bit ambiguous, so I like to spell it out. It's d by dt of dy dx over dx dt. Now you might think, if the first derivative, y prime, is the first derivative dy dt over the first derivative dx dt, you might just think, oh, for second derivative, I'll just put the second derivative, d squared y dt squared, over the second derivative, d squared x dt squared. But that's not the case. All right, so I think these formulas will make more sense when we use them. So here we go. Suppose c is given by this equation right here. So this is x comma y. Find the slope when t equals 1. So we start by just finding the slope in general. The slope is dy dx, which is dy dt over dx dt. I always start by stating the formula I'm going to use. All right, dy dt, think of this as t to the 1/2. So to take the derivative, we bring the 1/2 down and subtract 1 from the exponent. So that's going to give us 1 over 2 root t. Because we'll do a little bit of scrap over here. We want t to the 1/2 prime. That's 1/2 t to the negative 1/2. Which I wrote over here without negative exponents. Dx dt is going to be the same thing. You have to use the chain rule after you take, 1/2, and then the new exponent is negative 1/2. You multiply by the derivative of the inside, but the derivative of the inside is 1. So dx dt is 1 over 2 root t plus 1. All right, so multiply by the reciprocal, and we get the 2's cancel, and we get root t plus 1 over root t. And I'll just leave it like that. I could combine it all underneath 1 square root, but I'm just going to leave it like that. And now our slope when t is 1, I'll call it m. That's dy dx at t equal 1. So that's the square root of 1 plus 1, which is 2, over the square root of 1, which is root 2. And I'm calling it m because I'm going to use that slope in the point slope formula down below, or right here, when we find an equation of the tangent line. Okay, so remember point slope is y minus y naught equals m times x minus x naught. Well, I've got my m. My m is root 2. That's the slope of the curve at t equal 1. I need my x naught, y naught. So I go back to the original equation up here, and I plug 1 in for t, and that's going to give me root 2 comma 1. So now I've got the ingredients for the point slope. Y minus 1 is root 2, that's m, times x minus root 2. Let's clean that up. put it in slope-intercept form. Y is root 2x. Let's see, that'll give me minus 2, and then I'll add 1, so I'll get minus 1. Eliminate the parameter and graph the curve. Okay, so when you're eliminating the parameter, in this case, go back to the first page, we're going to use method 1, solve one equation for t and plug it into the second equation. Okay, so the question is, which equation do we want to solve for t? Let's see, I think I'll solve this one for t. This gives me t is y squared. And now plug that into here. X is the square root of y squared plus 1. All right, well, if we want to graph this, we're going to need to rewrite it so that we can recognize what it looks like. So square both sides. X squared is y squared plus 1. And then this is a hyperbola because it's x squared minus y squared equals 1. So when I set y equal to 0, x is plus or minus 1. So this one opens right left rather than up down. And I can't set x equal to 0. Okay, but how much of that hyperbola are we actually getting? The original parametric curve was given for t positive. So t greater than or equal to 0. When t is 0, let's see where we are. Xy would be square root of 1 is 1, and then the square root of 0 is 0. So I'm right there when t is 0. And now the question is, as t increases, am I going up this way or down the other way? I think I'm going up, but let's just check. Pick any number bigger than 0, like 1. Xy is root 2, comma 1. So indeed, I'm going this way because root 2, 1 is up here. All right, so now I suggest you pause the video and try this one yourself. And now we'll go through the solution together. Find the slope dy dx. So again, I like to start off by stating the formula I'm using. Dy dt over dx dt. Dy dt is 1 over t. Dx dt is negative 1 over t squared. And I got that by thinking about 1 over t as t to the negative 1 and using the power rule. Okay, and if we clean that up, that's negative t. Find the tangent line at t equal 1. Well, at t equal 1, we need two things. We need x naught, y naught, and we need m. So we need the slope and a point on the curve. So m we're going to get by taking our answer to part A and evaluating it when t is 1. So that's negative t evaluated when t is 1, which is negative 1. Okay, and then x naught, y naught is going to be x evaluated at 1, y evaluated at 1. Okay, so I go up here and I look at x and y. X is 1 over t, so 1 over 1 is 1. And y is negative 2 plus ln t. So negative 2 plus ln 1. ln 1 is 0, so I'm at 1, negative 2. So maybe here. Okay. And then point slope, y minus y naught, so y plus 2, is negative x minus 1. So that gives me y equals negative x plus 1, but then minus 2, so minus 1. So I've graphed the curve for us using Desmos, and then this is the tangent line, and it certainly looks reasonable, negative slope and a negative y-intercept. Okay, find the second derivative. So this is our first opportunity to use the second derivative formula. and it uses work from the first derivative. So I want d by dt. The first derivative is up here. It's negative t. And then I divide by dx dt, and we already did dx dt, it's down here. It's negative 1 over t squared. So I take the derivative of negative t to get negative 1, and that's over negative 1 over t squared, which is t squared. So you have to take the derivative of the answer in the first part and then divide again by dx dt. Okay? And finally, eliminate the parameter to find a Cartesian equation for the curve. So we're going to use method 1 again. So it looks to me like it would be easiest to solve for solve this equation for t. That gives me t is 1 over x. And then plug that into this equation. And that gives me y equals negative 2 plus ln of 1 over x. Okay, I want to show you how to graph this. So let's rewrite it as negative 2 minus ln x. And the way I did that was, I'll do my scrap paper over here. ln 1 over x is ln 1. Using properties of logarithms, ln 1 minus ln x, but ln 1 is 0. Okay, so evidently this curve looks like this green one up here. So if you had to, if you're stranded on a desert island and you had to graph this, you actually could. So here's y equals ln x. Just do it in steps. And this actually never intersects the y-axis. And then let's go to y equals negative ln x. That's a reflection of this curve about the x-axis. So it looks like that. And then finally, y equals negative 2 minus ln x takes this graph and moves it down 2 units. And so we get the green curve that you see up there. Okay, so I'm going to end this video. Here's a practice problem for you to do. And the solution is carefully written out at the bottom of the page, so don't look at it till you actually do it. And then we'll pick up part 2 of the video. We'll pick up with finding arc length, which are the formulas on the next page.